too.
Okay. Yeah, I think, Dustin, did you make good progress on problem one last night? And Jesse, I think you were online when I was working on problem one a little bit too
So
last night.
problem one, I got earning difference of 827K. Is that what everybody else got?
I'll show you.
Difference in,
Yeah, so basically 828,000, a little shy of 820,000. You had what I would call the struggle bus when I was watching your energy storage yesterday about figuring out why the revenue for the stored energy sold at peak is 4 million or 4.14 million.
Well, so what we're looking at, and I think these two rates should make sense to you based on, what we know about energy production. So it's going to be less expensive during non-peak, because they want to get rid of that electricity. One of the things in the reading for 214 was saying that electricity, when it's made, has to be used right away, or it gets wasted, or it has to get stored, or causes a blackout or a brownout, right? So, thus there is an incentive to sort of keep the grid running at a smooth, continuous rate. And I think you can probably appreciate that from an efficiency standpoint too, because in general, your car or truck likes to run at a continuous rate. Stopping, starting is additional load. So, but that said, if everybody's running during the peak hours, it's more expensive for the maintenance of the grid. There's more likely of something breaking and emergencies happening. So thus the justification for these two different rates. So in this particular case, we're looking at a farmer or rancher with a 100 megawatt. Wouldn't be a 100 megawatt turbine. They're not that big.
Well, that's what I was saying. You would need like 66 point something.
Yeah.
1.5. So
Right.
it's like GE. So
Right.
maybe like 1.8 or something.
So this is the total capacity of the wind farm.
I think like 2.
And it's running at about 27%. So in order to get the annual energy, all we're looking at is, so we got obviously megawatts, which is power. We're looking at megawatt hours. We're just multiplying by the number of hours in a year. The capacity factor is 27%. So that ends up giving you your annual energy. Of this, 30% is made during peak, 70% is made during off-peak. So the peak revenue is simply how many megawatt hours you're going to make in a year, what fraction is made during the peak, and then how much you can actually charge for that. So that's a pretty good chunk of change. The non-peak, you're not getting paid as much. And so this is from the supply side. And so the grid operator, the utility, is not going to want as much non-peak electricity, so they're going to pay less for it. Just simple supply and demand economics. Add those two numbers together, and there's the total that you could make from your 100 megawatt array. What is that going to be? I want to put that in dollars per kilowatt hour, right? Because a lot of times, we know what our dollars per kilowatt hour or cents per kilowatt hour. So let's actually just go ahead and figure that out. So equals. Well, first let's convert this to kilowatt hour. So equals. Here's your megawatt hours times 1,000. So we just converted megawatt hours to kilowatt hours. Do a control 1 on that. Number 0, decimal places, commas. So 236,520 kilowatt hours. And then we'll look at how much money you're sort of making selling to the grid. So equals dollars per kilowatt hour equals, put this down here, 3 cents, control 1. Let's give it one more decimal place. Yeah, right around 3 cents. So that makes sense, right? The utility is literally the middleman, and this particular rancher is the primary energy provider, so we're looking at dollars per kilowatt hour. So if Northwestern Energy then goes and sells it for 6 cents a kilowatt hour, they're doubling their money. If they sell it for 10, they're tripling it. So it makes sense, about the right range. Okay, and then on this guy, what the farmer has now done, let's make a little picture of this. So during non-peak hours, the wind is still blowing, and you're still doing that 70% of the time. So what he's going to do, it's going to be just the same scenario. So during peak hours, just like in scenario 1 with no storage, he's going to take, and in the second scenario with storage, just go ahead and sell it straight up. So there's no difference on that. But he's making electricity, or he's pulling energy from nature during non-peak hours. He's got it, but he doesn't want to sell it now because it's not as valuable now. So what's he do? He builds a giant underground cavern. Here's your wind turbine. Big array of them. So here we go. During non-peak hours. And he's going to take and dump this number. Where did that come from? Well, it's the total annual energy with the capacity factor built in. Little, kind of a subtle averaging thing here. There's no weather factor built in here. This is just one big average. I mean, it could actually be that during non-peak hours, you're actually getting better electricity. Thus, even more of an argument to build this pump storage. Guys, what's the energy capacity for air?
Depends on what elevation.
Well, we're sort of creating a very low elevation here. We're creating pressures that you wouldn't see at normal atmospheric pressure. What's the equation for how much energy you can store in a compressed tank? You guys remember that at all?
A tank?
Yeah, I mean, if you looked at a tank and what two numbers would you need to know to know how much energy is inside an air tank? Pressure. Throw again. Okay, one's pressure, so energy equals pressure and volume. There you go. That's all it is. Pretty simple. More, higher pressure, more energy, bigger volume, more energy. And what are the units we're going to use on this guy? What are the SI units? Pounds are imperial.
So pascals?
Pascals, there you go. So let's just do one quick little calculation here. So if we had, first of all, P, what's atmospheric pressure?
1.
one bar, but it's, so it's 14.7 PSI equals, it's about 101,000 pascals. And a pascal is the same as 101. Oops. So the dimension on pascals equal that many newtons per square meter. Or, here's another way to think of it, and this is a little bit strange, equals 101,000 joules per cubic meter. Where the heck did that come from? So I just so I just multiplied the top and bottom by a meter, which is the same as multiplying by 1, and a joule is a Newton meter. So essentially, pressure is not only force per unit area, it's also energy per unit volume. Okay, so from there, just multiply by how many cubic meters you have, and that's your energy. Pretty simple, straightforward. Okay.
Is that how you calculated the energy?
The problem doesn't ask for that information,
Okay, I
but
was gonna say, like,
no, we didn't go there. But let's just say you're out there and you're advising a rancher, like, well, how big a tank do I need? Well, the question would be, how much pressure can the vessel withstand? And any pressure vessel is going to have a rating after which it's going to rupture. So you say, well, you can hold whatever remember the
500 atmosphere.
Yeah.
500 station.
So from that, you can see how many atmospheres, how many pascals those tanks, it was 350 atmospheres that those bad boys could hold, multiplied by the volume, and that's how much energy you could hold. And that's just mechanical energy, right? This is purely mechanical. If we were putting hydrogen in there, it would actually be chemical energy as well because you're going to burn it. Okay, so that's how you calculate the energy on that guy. So back to this, the whole point is, this is how much non-peak energy you're going to make. Now, what's that?
The efficiency of the
What's the efficiency of the system?
energy storage.
Right, because what's going to happen is you got to run your pump. That's going to suck off some energy, and then maybe you've got a pump that's also a turbine, or maybe you have a pump and a turbine. Let's just say you got both. Turbine. Pump's going to take off some energy, and so is the turbine. So you're going to lose half of it in your transaction. But the nice thing is, you're getting more than double your money. But so if we go back in here and just play around a little bit, here's $40. You break even with these particular numbers. Does that make sense? So if it were not the case that your peak were not more than double and your efficiency is what it was, you wouldn't bother economically with the storage tank. It's just kind of one extra level of complexity that's not going to get you any extra. Sound good? So we're good on problem one? Good? Okay, let's do problem two.
We estimated that the energy storage could be installed for $7 million should the project be funded with the assumption there's no operating maintenance costs. The market value remains the same. Life of the project is 10 years.
Oh.
The discount rate is 6%.
Oh.
So he wants to put in those.
Is that also part of problem one?
That's just what he commented on that post for it.
Oh, okay.
Did that this morning.
Oh, did
Yeah.
Yeah, I mean, it's online, it's on the forum.
Okay.
Everyone, and I don't know if I did it right.
I think we can just go back to our financial functions to solve it though, right?
Yeah, I just did the annuity annually times PV 6%, 10 years, times -1.
Mhm. What's the capital cost again?
7 million. The PA of the revenue is 6.09 million. So the present value would be maybe 900,000, right?
The PA is what now?
6.092.
So these are both dollar. Oh, that's the number you came back with after you ran it through your function?
Just of the annuities, the present value of the.
Oh, I see.
the Production.
Okay.
From the production value per year.
Oh.
When you're,
So it sounds like your capital cost is greater than what your present value is, so it sounds like you wouldn't do it.
so you put in the 827 thousand into
Yeah.
that function.
Times PV of the interest rate.
Well, you would just use the interest rate in the year. You don't even focus on the 7 million, besides that being a negative factor in the beginning.
Yeah,
Yeah. So
I
you-
didn't use it in my
Okay.
calculation. I
So-
just subtracted 7, or this 6 million from 7 million, and got another one.
yeah.
Or the other way around.
What function did you use?
PV,
The
present value,
Present value of the annuity. What was the discount rate?
6%, period was 10 years.
Mm-hmm.
And I think no operation and maintenance costs. If you put, let's say you're only, I don't know how much pressure it would make to make sense, but you have to be putting a couple thousand PSI into these cabinets. You're gonna have a rupture of one of the cabinets.
Well, it's basically what I put, in my opinion, the energy storage option would not be economical even with the lack of maintenance fees. I mean, shit, I mean, start
I
adding
mean-
maintenance fees in there.
I mean, because you're talking about, you're telling me that there's not one rupture or 1 week going to leak out, a couple thousand PSI.
Probably not. What, give me your numbers again on this one?
So the amount is 827,820 is the annual profit revenue.
Where do you get that?
The difference between what the wind farm.
Oh, okay,
earnings
okay, sweet,
without-
all right.
Without energy storage and wind farm earnings with energy.
Gotcha, okay. Oh, you ran the difference on these two guys, right?
Yeah, difference on the total.
Equals dink minus. So you're looking at that as your annuity.
Yes.
Copy.
And then the initial capital's 7 million.
Right,
So then the discount rate's 6%.
Right.
So yeah, I got the.
okay, so your present value of that annual investment is that,
And then the initial capital is 7.
yeah. So the present value of your investment is less than whatever your cap. So what if you ran it for longer?
It should be better, way better.
Yeah.
So then it would.
So the 10 years,
I think.
maybe so your 10 years might be the
Rupture point.
it might be the mean time between failure point, if you're familiar with that term. It's,
So you're talking about when things wear out?
well, yeah, and things wear out on a random basis. It's on a, well,
We
this
got
is,
you.
this is the weirdest thing. I've got a paper out there in the Naval Engineers Journal, and that thing gets cited more than all of our other papers combined. So, it's just about mean time between failure. And it was written to decide how much extra junk you want to take on board your Navy ship to make sure that you don't have too much, but you got enough.
So people cite.
That's all it was. What's that?
I mean, because they have those graphs for cars, so
Yeah.
per mileage driven,
Yeah.
like for every component that fails.
Yeah. So what you would have to do is put that number is basically when your system becomes junk, when you can no longer make that assumption of no maintenance, et cetera.
But if you put in there,
This is where the insurance companies start to get you, right? Same thing with your heart valve, your liver, what's the mean time between failure?
I mean, the interesting thing, do that is just copy that into the actual problem one, and then see how many megawatts you would actually have to build it to
Oh, there you go.
for the wind farm.
Yeah.
To make the energy storage system
Pay for itself.
be a viable option.
Yeah.
So
Cool.
it's cheaper on the front end to add 2 more wind turbines,
Mm.
make it a, 103 megawatts on the front
There you
end.
go.
And that would cause the difference in earnings to go up because you're making more, but then your capital costs for building your whole energy storage.
Yeah, yeah.
Because it's not going to make it any bigger, but you have the ability to.
Yeah, it's a good problem. It's a good problem. Okay, so let's,
Yeah, let's
we're a
go.
half hour in. I'll pull the plug on that and we'll go to problem 2.
Yeah, problem 2 is what you.